All right. Hi, everyone. Let's see. So last time we had started talking about double integrals, multiple integrals. Let me share this. Actually, yeah. And so if you look at this, I do have a handout here. It's actually going to be a decent amount of group work today. I just kind of want to talk a little bit about the idea again of doing an iterated integral. And then I'd like to kind of show you how we do it when an integral when the region is no longer a rectangle. Okay, so because that seems kind of scary. Like that's the real, like when we integrated over a rectangle last time, right? And that was not bad. But how do you do different shaped regions, and then how do you do kind of general regions? So let's just remind ourselves where we are. Stop the share. Okay. So we're talking about double integrals as iterated integrals, meaning we sort of do just two integrals in a row, two single integrals in a row. And last time we had an example, which was the function x squared y over the rectangle R. Someone remind me what the bounds were. I know I had negative, I think I had -2 less than y less than 4. I changed it because I had -2 to 2 and got 0. What are the x bounds? Was it 1 to 3? Yeah, I thought it was 1 to 3. Okay, so you could write it that way, like, yeah, 1 less than or equal to x less than 3. You know, I could write it as, I think I read it last time as this, which you think of just two closed intervals, sort of like in the plane. Those are the same thing. And let me just remind you, so we had the integral, well, okay, so here was the region. Actually, let me draw it correctly. So we had from 1 to 3, and we had from -2 to 4 in the y direction. And we had this this rectangle, right? And I think, actually remind me which way we did it last time. What was the, I know we did it one way. I just wanted to do it the other way and see that we got the same answer. So what did we do? Was the inside integral x equals 1, x equals 3, or was that the outside integral? In your notes from last class. X was inside. So if you think about it, that means we were sort of integrating this function over a slice, right? You've got to imagine the surface is out here about, like, now z is pointing this way. And so the surface is somewhere out here. And we kind of, one way to think about this integral is that we want to cover every point in this region. Just like when we integrate from like a regular function from like 1 to 3, we would integrate every point. We kind of cover every point between 1 and 3. Right, so we're trying to cover every point in this region. So the integral, if we want to write it this way, there's sort of a little dA patch everywhere, right? Like there's a dA, there's dAs all along here, which are these little tiny square patches. But then there's also DAs sort of everywhere. But in some ways, it's just a matter of organizing how we're gonna cover all the little patches of this region. I guess I should say this is R right here. And we want to add this up. I mean, if you imagine this coming from like a Riemann sum, right? You can imagine this coming from some Riemann sum where it's like f of xi, yi, delta a, I equals whatever to whatever. But we want these delta a's to cover the entire, we want to cover all of R. Just like we cover an entire interval with delta x's when we do single integrals, right? And so that's kind of what I'm trying to say here is that then it's like, how do you organize? I mean, this really is kind of like, how do you even organize a sum like this? It's really easy in one dimension. But the idea is we're going to organize it by doing it in sort of like rows, right? We're going to add up rows first, and then after we add up each row, we can then add up, we can add up along, and maybe I should say it this way. We can add up along an individual row, and then we can add up all the rows. And that's going to give us the sort of like the total, this total sum. So we organize covering all of R. So I guess I could say this too is going to sort of cover all of R. And we organize by, so last time, we organized this by adding all the DAs in a given row. So that's y equals constant. And then we added all the rows. And added up all the rows. So in a Riemann sum, that would literally be addition. When I say adding here, though, I sort of mean like integration, right? So we had, let me just write it this way. So we had i.e., this integral, we organized it in the following way, which is that we integrated from 1 to 3 first. I guess this is the function x squared y. I could go ahead and put the function in. And so that's x equals 1 to x equals 3 dx. And then we did y equals -2 to y equals 4 dy. And this was sort of like integrate along a slice. A horizontal slice. Horizontal on the xy plane. And then this whole thing was add up all the slices. Does that make sense to everyone? It's kind of what we did last time. That was supposed to be the straight import of this. Is that like, we're trying to sort of add up all the values of the function over the whole region. And so we have to cover the entire region. This is how I conceptualize the double integral. Now we could have done it the other way. What did we get, by the way, when we did this? What was the, we got a number, right? Did we get a number? Did I finish off? Yeah, we got a whole number, right? What's that? 52. So if you work this out, it equals 52. We could slice the other way. We could have done, x equals constant slices first, which are vertical in the xy plane. So let's just check and see that we get the same answer. Yeah, this was from last time. So let's just do this the other way. So the other way would just be the inside would be the integral. So I guess they're really x equals constant slices. Right, so each slice would be like a vertical slice in that picture up there. It's worth drawing a vertical slice just to make it clear. That's supposed to be vertical. So the inside integral would be from -2 to 4. In fact, you're really just switching the bounds, kind of, right? Except now this is a dy integral because we're integrating up and down. So in dy. And then the outside integral is from 1 to 3 dx. Okay. And let's just see that we get 52 again. Let's just see if this makes sense. So remember what we do is we start from the inside integral. We could say, well, okay, we're treating x like a constant, right? We integrate respect to y. It's like partial integration kind of. And so this is what, 1/2 x squared y squared from y equals -2 to y equals 4. So that's 1/2 x squared times 16 minus 4, maybe. 4 squared minus -2 squared, which I think is 6x squared. Wait, did I do math right? 16 minus 4 is 12. Yeah, half of 12 is 6. Okay, so then that just becomes the integral from x equals 1 to x equals 3 of 6x squared dx. Yeah. Does this work? What's the integral of 6x squared? 2x cubed from 1 to 3, which is 2 times 27 minus 1, which is 2 times 26, which is 52. Okay, so that's nice. That's satisfying. Worked both ways, right? It didn't really matter which way we integrated. Questions about that? Does that make sense what we're doing? Any of the steps weird? It's kind of nice how all the y's go away from the inside integral. Because if you think about it, it's almost like this pink line right here. People can see on video. But, oh yeah. So this line, it's like the individual slice was adding up along this line. So that was y equals -2 to y equals 4. And then we had to add up the slices. So there's a bunch of these, there's infinitely many of these little vertical lines, and we're sort of adding up the leftmost slice to the rightmost slice. So again, this is like each slice. This right here is the bottom of the slice. This is the top of the slice. This is the leftmost slice. This is the rightmost slice. Right, I'm really thinking of covering this region with these kind of the idea, covering this region with those slices, right? So there's the leftmost slice, the rightmost slice. This is I'm belaboring this because it's going to be important in a minute. This is the bottom of a slice. This is the top of a slice. Right, we want to do each slice, so we go from the bottom of the slice to the top of the slice, and then we want to go add up the slices, so the leftmost slice to the rightmost slice. Here you could be like, this could be the left-hand endpoint of the slice, like that's the horizontal slice, left-hand endpoint to right-hand endpoint of the slice, bottommost slice to topmost slice. Make sense? Okay. The reason I'm belaboring that is because I want to think about what if our region is not rectangular. So let's do an example with a non-rectangular region. So we can do the same function. It doesn't really matter. What if instead of this rectangle, I wanted some sort of like triangle or something? So let's try that. So rectangular regions. This deserves more question marks and maybe an exclamation point or two. Okay, so yeah, what if we had, let's just say this region. What if I had, what I had in mind was like, let's connect, here's a point, -1, 1. Here's a point 2, 1. And here's a point 2, 5. And if I make this region, so this is our R. Okay, and so it's kind of weird. I mean, if you think about it, it's like, so again, let's have the function integrate. Yeah, let's just do x squared y again over this R. Now, again, this is some surface, like this is an xy plane right here, but then this z, the function exists over this region, right? So it really is the volume under the curvy surface and above this triangle. Kind of strange, but that is some volume. You could picture that as some volume in space, right? And we want to find that volume. Now, the idea, though, is going to be sort of similar. That's kind of why I was harping on the slices thing here. Is like, what if we wanted to take, we want to cover this region, right? So what if we just do vertical slices? Let's try vertical slices. So we want to cover sort of R. Let's try vertical slices. Okay, the leftmost slice, this is where you really have to think about like leftmost slice, rightmost slice, bottom of each slice, top of each slice. If you want to sort of think about how you're covering this entire region. What's the leftmost slice? X equals -1. There's like these slices get tinier and tinier, right? So there's an x equals -1 slice there. The rightmost slice is x equals 2, right here, right? Here's the part's a little tricky. So bottom of each slice, well, this is not tricky. What's the bottom of each slice? Y equals 1, right? What about the top of each slice? This is the part that's weird because it's changing. Right? We can't just say now like, oh, it's 5, because it's only 5. The top of the slice is only 5 over here. But I think there's a way to find, like, what if we had this slice, like, what if I wanted to identify, like, what is this point right here? Anybody tell me? Sorry? Is it 7/3? Oh, it is. I meant to make a line of slope 2. You're right, I didn't make it a line of slope too, did I? I made it a line of slope. What's the slope, 4/3? Damn it, why did I do that? Okay. It's funny, I was gonna just draw the lines and then instead I just picked the points. Yeah, so if you go over 2 up 4, right? I could fix that if I wanted to, couldn't I? Let's make this 7. We haven't really used this number at all. Okay, sorry, that's what I meant to put there was 7. Now I think you can see you go over 3 up 6. So the slope's 2. So this would be 0, what? 3, right? We go up 2. If we went to 1, that would be 1, 5, etc. So if I took the slice, like if I took the slice at x equals 0, the top of the slice would be 3. If I took the slice at x equals 1, the top of the slice would be 5. If I took the slice at x equals 2, the top of the slice would be 7. So it's changing, right? But we're good, we're mathematicians. We can figure this out, right? What is, I mean, one thing we could do is we could actually give the boundaries as curves. Like this is the curve y equals 1, it's a line. This is x equals 2. And what about this? What's this line right here? What's the equation? In fact, you can probably just read it off now that we know the slope. Someone's muttering it under their breath. 2x plus 3, right? It's slope intercept. So it's 2x plus 3 is this line, right? So the top of each slice is actually y equals 2x plus 3. Right? Because that'll work. Like if you plug in 0, the top is 3. If you plug in 1, the top is 5. If you plug in 2, the top is 7. So the top is a function of x. It's changing, so it's a function of x. Right? It's a variable. And so what happens is when you write down the integral, then the integral over this region, x squared y dA, well, we have an inside integral and an outside integral. The inside integral is each slice. The outside integral is the leftmost slice to the rightmost slice. So that's x equals 1 to x equals 2, no, x equals -1 to x equals 2. This is the thing that's weird. This is y equals 1 to y equals 2x plus 3. So now you can have variables in your bounds of your integrals, which seems kind of strange at first, but right, it's kind of like what I was writing up there on the top board about like, it's still the same thing. This is the bottom. This is the bottom of each slice. This is the top of a slice. This is the leftmost slice. And this is the rightmost slice. And then we still have our function that we have to integrate, so x squared y. And then this is dy, and then dx. So again, the inside integral is the integral along one specific slice. This is the integral along a slice. Okay, so now this is something we can actually figure out. It's probably going to be a tiny bit nasty now that I'm looking at it, but we can, again, we can do it. Let me see. Okay, so sorry, this has really got very busy. Let me rewrite this so that we can actually evaluate it. Yeah. Again, please ask questions. I'll try to watch the chat if people have questions in the chat. Oh, I think this is the chat from earlier. Yeah. Okay, let me rewrite this again, and I should be writing bigger. So by the way, books often don't write the x equals y equals here, which means you have to really think about from context, like you have to match to the d, like the inside d matches to the inside integral. They also start to drop the parentheses and just kind of write it this way. So let's actually evaluate the inside integral. What do we get? Well, we saw this already in the previous example. It's that, right? But now we got to plug in 1 and we got to plug in 2x plus 3. So now it's going to be a more complicated function of x. But it'll still work, right? Like that. Just plugging in y equals 1 and y equals 2x plus 3. Does that make sense? People with me? Okay, so I need to FOIL this out probably. So this is 1/2 x squared times 4x squared plus 12x plus 9 minus 1 is plus 8. I may or may not have done that correctly. Please check me. That was quick. Oh, the 1/2, and that's nice. These are all even. Let's pretend I did that on purpose. So that's 2x squared plus 6x cubed plus 4x squared. I think is the inside integral. No, this should be a 4th power. Yeah. This is just algebra at this point. And then, so then we get something we can integrate, right? So we get the integral from -1 to 2 of this function, 2x to the 4th plus 6x cubed plus 4x squared dx. So sorry, this was all the inside integral. All this was the inside integral. Like that. Right. And now, I mean, it is just a matter of actually doing it and getting a number. But it's going to be something kind of unpleasant. But let's just quickly something like this. Maybe 1 to 2. I don't know if I did that right. 2/5 x to the 5th plus 3/2 x to the 4th plus 4/3 x cubed. Okay, so anyways, this is it's some number. Maybe I don't even care. But you can sort of see. You get some number from this. Okay. Makes sense. At least what the process is. The thing that's really interesting is just the idea of like drawing the region and setting up the slices. That's the part of this is interesting. The rest is just, single variable calculus, integrals and stuff. kind of cool that you can end up with like like a variable in the expression. But okay, we could have also done this with horizontal slices and see if we get the same answer. I do think we would have something ugly cubed if we integrated the x here first, so I don't necessarily want to do it. But you would have to, you would have to be, let me just think about it for a second. Actually, let's just set up. Let's not actually do the integral, but let's set up the integral with horizontal slices also. Okay. Let's think about how we would set this up with horizontal slices. You know, and then you could check on your own time if you want. You get the same answer either way, but it gets kind of, those integrals get kind of nasty. So, question. Chat. No questions in the chat. Okay. So what would the setup be if we used horizontal slices instead of vertical slices? Do it again with horizontal slices. So now we would have a slice that looked like this, right? This yellow slice right here. And so let's think about each slice. Again, even before I write down integrals, I just like to write these things out, like each slice and then add up all the slices. So now we have a leftmost or left endpoint. And we have a right endpoint. And now we have a bottommost slice. So I can draw a bunch of these horizontal yellow lines, right? And we have a topmost slice. Okay, so what's easy here? What's the right endpoint of any slice? X equals 2, right? All the slices end up at the same X value. What's the bottommost slice? Y equals 1, and the topmost slice? Yeah, they get smaller and smaller, but like they kind of go all the way up to y equals 7. Okay, so the outside bounds should not have variables in them. Like this is going to be the outside integral. And you want to get an actual number. So the outside, notice that integral up there that we did had an x, it had a variable bound on the inside integral. But if we want to get a number, the outside integral should have numbers on the bounds. Now this one is a little bit harder, but how do you find the left endpoint of each slice? Yeah, solve for x in terms of y here, because now it's like, right, we really want, at different heights y, we'll get different left endpoints, right? So if we solve for x in terms of y, what do we get? 1/2 times y minus 3, maybe something like that. Why is it a function? Well, it's all each slice, like on this slice, it's not, the left endpoint is not -1, right? At this point, the left endpoint is like around here. For this, if we took a slice up here, the left endpoint's, you know, a different x value. So the x value of the left endpoint changes depending on which slice we're looking at. Yeah, the leftmost slice, when we did vertical slices, the leftmost slice is sort of this degenerate, you know, they get tinier and tinier, and it's -1. But for each slice, right, that's what you're, yeah, so here, like when you're looking at slices, there are slices from y equals 1 to y equals 7. Or vertically, there's slices from x equals -1 to x equals 2. But okay, so that's, did I do that right? 1/2 y minus 3. And so this gives the left endpoint of any slice, left endpoint of the slice at height y. And again, you could check that when you plug in y equals 1, you get x equals -1. When you plug in y equals 7, you get x equals 2. When you plug in y equals 3, you get x equals 0. Right, you can sort of check. So this is the one that's kind of hard, x equals 1/2 times y minus 3. And now once we've written all this down, it's easy to write down the integral, right? The integral is just, and I won't even try to evaluate it this time. It's the setup really that's kind of interesting here. Sometimes it's nice to do the values and see that we get the same thing both ways, but it really is the setup. So we're going to do the outer slice. The outer integral is the adding up the slices. So that's y equals 1 to y equals 7. The inside integral is each slice. So that's x equals 2. Oh, no, I'm doing it backwards. Did I do this? Yeah, x equals 2 is up here, right? And the left endpoint is 1/2 y minus 3. And then we do x squared y, but now we do dx first and then dy, because dx should match the x, the inside integral. So the setup's all the geometry of the region. That's really what's interesting, is what are the bounds. Questions about this? Makes some sense. Okay. So there are problems on this handout. Maybe we'll just do problem 1, maybe just in groups, kind of sitting. If you guys want to work together, and you all want to work together, and you two want to work together, and some sort of groups of people over here, I don't work together. Just like think about. So this is a different. So this number 1 is. Let me share screen so people can see. But you can download, if you're remote, you can download the handout and see it. But because it's on the handouts page. But here it is. So number 1. So this is a different function, x squared plus y. Now this region is bounded by y equals x squared and y equals 4. And so what I want you to do is draw the region and then try to set it up with, I think vertical slices maybe is easier at first. And then actually do the integral and see what you get. And then you can also do it again with horizontal slices. So it's kind of a matter of what we just did. We just draw the region carefully. Does that make sense? Should we just do it? Should we just do it at our chairs? Do you want to go to the boards? Do you prefer? You prefer to go to the boards? Oh, good. All right, go to the boards and do it. Just to grab a couple people near you and go to a board. It is probably better. Go to the board. See if we can do this in the last 10 minutes. Those of you on the Zoom can either chat with each other, try to do it. Or I think there's, wait, sorry, I just want to see if there's a, there's a whiteboard. Let me see if I can draw with my mouse. You guys can work on this whiteboard together if you want. Actually, can you all use it, or is it only? Can other people write on this whiteboard? Or is it just me? Oh, somebody's. Oh, it's just me. I don't know how to make it shared so that you guys can write on it. Sorry, this is stupid then. Okay, I'll stop the sharing. I was thinking somehow we could all write on the whiteboard. But yeah, for those of you remote, just try it. And maybe compare notes with each other. I'm gonna pause the recording. Maybe I'll just resume the recording quickly just to point this out. This was the answers for this to number 1 with vertical slices and with horizontal slices. So just recording it for posterity. Thank you. All right. Yes, thank you everyone. Sorry to cut you off abruptly. But this afternoon, you have a down moment. Maybe you evaluate both of these and see that you get the same number. And then life is good. All right, thank you. All right, I'll stop recording.